And this is section 8.6, exponential decay functions, and we are on, let me write it down, page 531. You probably should pause the video real quick. Go to page 531. This is the last section of chapter 8. And exponential decay functions, this video won't be nearly as long as the 8.5 video. I had a lot to cover with exponential growth functions. And the reason this won't be very long is exponential decay functions are very similar to growth functions with one exception. Growth obviously means values are increasing over time. Decay means values are decreasing over time. So that's what I just had mentioned here. The good news that will make this video short is that these are pretty much the same as exponential growth functions. They're both in the family of exponential functions. Alright, so a lot of what we're talking about today will be the same. They both have the same equation form. Y equals A times B to the x power. Remember, this is what exponential functions look like. B is what we're multiplying each time to get that next y value in my table, just like we had the other day. So what is the difference? And we've already talked about that a little bit. In growth functions, you know, obviously we're growing from left to right, which means the b value has to be greater than 1. This value for b, if there's going to be growth, has to be a number that's greater than 1. In decay functions, the b value has to be a number between 0 and 1. In other words, it's got to be a fraction that's more than 0 but less than 1. If we have a number here that's a fraction more than 0 but less than 1, that means we will get a decay function. And a decay function in the graph, it's going to look different than growth. A growth function, remember from our last video, started real low, started near 0, and then once it passed the y-axis, it started growing rapidly. A decay function is going to, as we are negative for x left of the y-axis, a decay function, you can see it will start high and do the exact reverse pattern. It will start high, it will start decreasing, and once we get past the y-axis, here, then all of a sudden it's just going to keep on approaching and getting closer to 0 without actually touching 0. So you can see it's almost a reverse pattern. Here's growth, here's decay. Keep on going here. How does the a value, remember we talked about this in my last video, I had you take out your calculator and we were graphing, and how does the a value affect my equation y equals a times b to the x power in a decay function? And again, good news, it's exactly the same thing. The same effect that a had on the growth function happens on the decay functions. I think I'm going to show that real quick. And you can see I took my calculator out. Let's just quickly say that we have the decay function y equals, we'll use a as 1. So 1 times 1/2. Remember, a decay function, the b value has to be between 0 and 1. So I'll do 1/2 to the x power. There's my decay function. And when you take the graph and you look at it, you'll see there's that decay style graph that I already showed you earlier on in my previous slide. Well, let's see what happens if I were to make my a value not 1, but let's say I'm going to make it, let's make it something other than 1, like 3. So we have 3 times 1/2 to the x power. Let's see what happens here. And some of you might already have a clue what happens based on our last video, but you'll notice here's my previous function when a was 1. Well, you can see when a is 3, it's the same graph, it's just being stretched up. So a being greater than 1 is going to stretch the graph upward, just like it did on my prior video. If a is a number less than 1, like let's make a 1/2. So there's 1/2 times my b value is still 1/2 to the x power. Let's see what happens in this case. And again, I think some of you already know what's going to happen, and you can see it here. Okay, when a was less than 1, my graph shrunk. You can see it's now lower than it was previously. And finally, if I make a negative amount, let's just say we have negative 3 times half to the x power. When we do that, we will see that we have a reflection. So remember, when I had the graph of y equals 3 times half to the x power, it was this. Negative 3 times half to the x power is just the reflection of that. So negative values for a will reflect the graph. If a is greater than 1, it stretches the graph. If a is between 0 and 1, it shrinks the graph. So a value of negative 3, which you see, will not only stretch the graph, it will also reflect it. So and that's what we talked about in my prior video. So going back, so again, a does the exact same thing in decay functions as it does to growth functions. How is the decay formula for money, population, etc. different from the growth formula? And really, it's exactly the same with one minor exception. Here is the decay formula. Y is the amount you have at the end of the process. A is the initial amount. R is the percent rate written as a decimal. T is the number of time periods. And you're probably looking at this and saying this looks almost exactly the same, like the same formula we just used for growth. You probably already see the one major difference. I'll highlight it here in red. The only difference is in decay we have a subtraction here, not an addition. Okay? How do we write a rule for decay? And again, good news, it's the same thing we did prior. Remember, a linear function, if there's an addition or a subtraction pattern in our table for y, that would be linear. When there is a multiplication pattern for y, that is exponential. We can review that on page 531. Look at the top of page 531 where it says write a function rule. You can see in table A they gave us a sample of a growth exponential function, because you can see how in my table every time we add 1 for x we have to multiply y by 3. Since 3 is bigger than 1, b is 3, that means we have a growth function there. If you look at part B in this example, again, now sometimes people look at this and they're like, okay, I start with 4 and I get to 1 and then I get to a quarter, and they're thinking, well, if I divide by 4, let's try that. 4 divided by 4 is 1. 1 divided by 4 is a quarter, and so on. They're thinking divide by 4, which is right, but when we talk exponential, we want to think of multiplying. Dividing by 4 is the same as multiplying by a quarter, which you see in the book. So I hope you're looking at page 531. You can see they're showing times quarter, times quarter, times quarter. That means b is a quarter. Well, remember, from my first slide, if b is a quarter, that means b is between 0 and 1. That would be a decay function. All right? So when you look at the very bottom of page 531, look at this table. You can see the table. It's negative 1, 0, 1, 2 for x, 5, 1, 1/5, and 1/25 for y. Well, do you notice if you take 5 and multiply by a fifth, you get 1. If you take 1 and multiply by a fifth, you get a fifth. And a fifth times a fifth is 1/25. What I just figured out is that this is decay. It's exponential decay because I'm multiplying by a fifth each time. Again, remember, if you were thinking, wait a minute, I was dividing by 5 each time, that's fine. Just change that thinking from dividing by 5 to, hey, dividing by 5 is multiplying by a fifth, which means b is a fifth. And then to find a, remember, to find a, you look at your table. Do you see how on our table we have the point 0, 1? That's an easy point to work with. I will take x, which is 0. I will take x, which is 0. And I will plug in 0 for x, and I will plug in 1 for y, and when I do that, I'm going to get 1 equals a times, remember, anything to the 0 power is 1, so I have 1 equals a times 1, and as soon as I get 1 equals a times 1, I know that a must have been 1, because 1 times 1 is 1, so a must have been 1. So here are two ways I could write that final exponential decay equation, I could have put y equals 1 times the 1/5 x, or I could have just not even put the 1 in front, y equals 1/5 to the x power. And that's what we're doing on this section. We're just working on exponential decay. The questions you're going to work on are going to be the same kinds of questions that you did back in section 8.5. 8.5 was over growth, 8.6 is over decay. So the questions, if you look on page 535, you're going to see the same kinds of questions. Okay? Like if you look at numbers 3 to 6, they're going to ask you to write a rule for the table if it's exponential. Okay? Tell me if the table's exponential, then write a rule. Same kind of problems that we did back in 8.5. They're going to have you graph in 7 to 18 exponential decay functions. You're going to identify the domain and range. Again, same kind of stuff we did back in 8.5. They're going to have you compare a function to the graph of another function like they do in 20 to 31. They're going to have you compare the function listed with the graph of y equals 1/4 of the x powered. Same kind of stuff they had you do back in 8.5. I wanted to give you, before I turn this off, one quick example, real-life example of where you would see exponential decay, and I just typed in a little search, exponential decay graphs. With the growth, I showed you money, and here would be a good exponential decay example, and it's over radioactive curves and calculations. When I went to, and you can see it here, radio decay, radioactivity decays in an exponential manner, exponential decay curve. So when you have some of the, I don't know if you're too young to remember Chernobyl or some of these things where we had nuclear plants and they overheated and it was a big nuclear catastrophe and the radioactivity and so on, there's a radioactive curve that the radioactivity drops at, and that would be based on exponential decay. And you can kind of see that happening here. In fact, if I take my pen, let me just draw over this for a second. If I take my pen, and you can see, you know, we have a definite, it's not very good, not very well drawn. Let me try again. Try better. You can see we have this type of pattern where if it kept on going, it's eventually going to go towards 0 and just keep on going closer and closer to 0, even though it will never touch 0. Okay? So that would just be one example of exponential decay. Radioactivity declines at an exponential with, or I should say it again, radioactivity is an exponential decay function. Okay, I'm going to stop the video here. That's long enough. If we have questions, we can go through those things tomorrow.